A conducting non-magnetic ring is placed over a solenoid, which is a long coil of wire wrapped in many turns. The solenoid is connected to a power source which produces alternating current and initially is switched off. Once the power source is switched on, the ring that was initially resting on the solenoid flies off, as you can see in the animation. If we take an identical ring, but this time it has a slit along its cross section, nothing happens once the power is turned on. So, why is this the case? We will solve this puzzle of the jumping ring using Faraday's and Lenz's law discussed in the next part of the video. To understand this phenomenon, it is first essential to discuss the notion of electromotive force, more commonly referred to as EMF. Despite its name, the electromotive force is not actually a force, but is the energy provided by a device to maintain a steady current in a coil. And a good example of an EMF source which you have encountered is a battery. The battery is going to supply EMF by transforming chemical energy into electric energy. It should be noted, however, that there are numerous sources of EMF other than batteries. For example, due to the phenomenon known as electromagnetic induction, which will be our main focus in this video. In 1831, Faraday discovered that EMF could be generated in a conductor by changing the magnetic flux in a closed loop. We could define magnetic flux as the component of magnetic field passing perpendicular to a given surface, which is just the dot product between the magnetic field vector and the unit vector normal to the surface. The notion of flux is closely related to the area considered. Therefore, we can change the magnetic flux not only by changing the magnetic field, but by changing the surface that it goes through. For example, the magnetic flux through a coil can be changed if we expand or reduce the coil, or by rotating it relative to the field. Faraday states by changing a magnetic flux interacts with an electric field to produce electromotive force, and hence to produce a current. This phenomenon is known as electromagnetic induction. The magnitude of EMF in a conducting loop is related to the rate of change of magnetic flux through this loop. By Faraday's law, the electric field along the closed loop is the negative time derivative of the flux going through the loop. In 1834, Lenz, a Russian scientist, formulated Lenz's law, which tells us that the induced EMF is always in the direction as to oppose the change in flux that caused it. An example of this is when a magnet moves into a loop of wire with the north pole first. The increasing magnetic flux through this closed loop induces an EMF and therefore a current in the wire. The direction of this current will be such that it will produce a magnetic field to oppose the increasing flux. So the induced magnetic field will be harder for the bar magnet to pass through by repelling it. The right hand rule, where the thumb points in the direction of the current and your fingers wrapped around, allows you to find the direction of the induced current. To better understand Faraday's law, let's consider some examples. Imagine a uniform magnetic field in the given area pointing out of the screen with a rectangular conducting wire in the position shown in the diagram. The wire has a length L and a width W. The wire is moving to the right with a velocity V. So what is the induced EMF? The flux through the wire is the uniform magnetic field B multiplied by the area. So the width times the change in displacement. So phi is the magnetic field times the width, and after differentiating we find EMF. Because flux through the rectangular conductor is decreasing, there will be an induced current inside to oppose this change. By the right hand rule, this current will flow counterclockwise and create a magnetic field pointing out of the page. So now we understand all the concepts, let's put them together and return to the puzzle. When the alternating current starts flowing, the solenoid induces a time-varying magnetic field as shown in the diagram. This means that now we have the magnetic field which changes the magnetic flux through the ring, which is not magnetic but is conducting. By Faraday's law, the flux through the ring induces a current in the ring, and so now the ring itself is a magnetic dipole and therefore has a magnetic field associated with it, which is denoted by black arrows. By Lenz's law, we know that the current of the magnetic field will oppose the change in flux. The poles of the two magnetic fields will oppose each other, causing the ring to jump as it continues to try reduce the flux through it. As you can see, the magnetic field from the ring comes closer to the solenoid, which causes this jumping motion seen in the diagram. Note that if the ring has a slit through it, the current will not flow and therefore nothing will happen. So now let's summarize everything. We discussed the EMF and some of its sources. We reviewed the idea of magnetic flux and introduced Faraday's law of induction. And we reviewed Lenz's law by giving an example. We united all of these concepts and we spoke about them in order to understand them better. And finally, we explained the jumping ring puzzle using our knowledge. I hope you understood everything. Thank you.